All right, this is the Helicopter Flying Handbook, Chapter 11, page 16 of 24, System Malfunctions. The reliability and dependability record of modern helicopters is very impressive. By following the manufacturer's recommendations regarding operating limits and procedures and periodic maintenance and inspections, most systems and equipment failures can be eliminated. Most malfunctions or failures can be traced to some error on the part of the pilot. Therefore, most emergencies can be averted before they happen. An actual emergency is a rare occurrence. Anti-torque system failure. So anti-torque failure usually falls into one of the two categories. One is failure of the power drive portion of the tail rotor system, resulting in a complete loss of anti-torque. The other category covers mechanical control failures, prohibiting the pilot from changing or controlling tail rotor thrust, even though the tail rotor may still be providing anti-torque thrust. Tail rotor drive systems include the drive shaft failures, tail rotor gearbox failures, or complete loss of the tail rotor itself. In any of these cases, the loss of anti-torque normally results in the immediate spinning of the helicopter's nose. The helicopter spins to the right in a counterclockwise rotor system and to the left in the clockwise system. The discussion is for a helicopter with a counterclockwise rotor system. The severity of the spin is proportionate to the amount of power being used and the airspeed. An anti-torque failure with a high power setting at a low airspeed results in a severe spinning to the right. At low power settings and high airspeeds, the spin is less severe. High airspeeds tend to streamline the helicopter and keep it from spinning. If a tail rotor failure occurs, power must be reduced in order to reduce main rotor torque. The techniques differ depending on whether the helicopter is in flight or in a hover, but ultimately require an autorotation. If a complete tail rotor failure occurs while hovering, enter a hovering autorotation by rolling off the throttle. If the failure occurs in forward flight, enter a normal autorotation by lowering the collective and rolling off the throttle. If the helicopter has enough forward airspeed close to cruising speed when the failure occurs, and depending on the helicopter's design, the vertical stabilizer may provide enough directional control to allow the pilot to maneuver the helicopter to more desirable landing site. Apply slight cyclic control. Opposite direction of yaw compensates for some of the yaw. This helps in directional control but also increases drag. Care must be taken not to lose too much forward airspeed because the streamlining effect diminishes as airspeed is reduced. Also, more altitude is required to accelerate to the correct airspeed if an autorotation is entered at low airspeed. The throttle or power level on some helicopters is not located on the collective and readily available. Faced with the loss of anti-torque, the pilot of these models may need to achieve forward flight and let the vertical fin stop the yawing rotation. With speed and altitude, the pilot will have the time to set up for an autorotative approach and set the power control to idle or off as the situation dictates. At low altitudes, the pilot may not be able to reduce the power setting and enter the autorotation before impact. A mechanical control failure limits or prevents control of tail rotor thrust and usually caused by a stuck or broken control rod or cable. While the tail rotor is still producing anti-torque thrust, it cannot be controlled by the pilot. The amount of anti-torque depends on the position at which controls jam or fail. Once again, the techniques differ depending on the amount of tail rotor thrust, but an autorotation is generally not required. The specific manufacturer's procedures should always be followed. The following is a generalized description of procedures when more specific procedures are not provided. So we'll go into landing the stuck left pedal. A stuck left pedal, high power setting, which might be experienced during takeoff or climb condition, results in the left yaw of the helicopter nose when power is reduced. Rolling off the throttle and entering an auto rotation only makes the matters worse. The landing profile for a stuck left pedal is best described as a normal to steep approach angle to arrive approximately 2 to 3 feet landing gear height above the intended landing area as transitional lift is lost. The steeper angle allows for a lower power setting during the approach and ensures that the nose remains to the left. Upon reaching the intended touchdown area and at the appropriate landing gear height, increase the collective smoothly to align the nose with the landing direction and cushion the landing. A small amount of forward cyclic is helpful to stop the nose from continuing to the right and directs the aircraft forward and down to the surface. In certain wind conditions, the nose of the helicopter may remain to the left with 0 to near 0 ground speed above the intended touchdown point. If the helicopter is not turning, simply lower the helicopter to the surface. If the nose of the helicopter is turning to the right and continues beyond the landing heading, roll the throttle toward flight idle the amount necessary to stop the turning while landing. If the helicopter is beginning to turn left, the pilot should be able to make the landing prior to the turn rate becoming excessive. However, if the turn rate begins to increase prior to landing, simply add power to make a go around and return for another landing. All right, now we're on page 17 and 24. Landing stuck, neutral, or right pedal. The landing profile for a stuck neutral or stuck right pedal is a low power approach terminating with a running or roll on landing. The approach profile can be best described as a shallow to normal approach angle to arrive approximately 2 to 3 feet landing gear height above the intended landing area with a minimum airspeed for directional control. The minimum airspeed is one that keeps the nose from continuing to yaw to the right. Upon reaching the intended touchdown area and at the appropriate landing gear height, reduce the throttle as necessary to overcome the yaw effect. If the nose of the helicopter remains to the right of the landing area, the amount of throttle reduction will vary based on power applied and winds. The higher the power setting used to cushion the landing, the more throttle the reduction will be. A coordinated throttle reduction and increased collective will result in a very smooth touchdown with some forward ground speed. If the nose of the helicopter is to the left of the landing heading, a slight increase in collective or aft cyclic may be used to align the nose for touchdown. The decision to land or go around has to be made prior to any throttle reduction. Using airspeed slightly above transitional lift may be helpful to ensure that the nose did not continue on to the right. If a go-around is required, increase the collective too much or too rapidly with airspeeds below transitional lift may cause a rapid spinning to the right. Once the helicopter has landed and is rolling to the stop, the heading can be controlled with a combination of collective, cyclic, and throttle. To turn the nose to the right, raise the collective or apply aft cyclic. The throttle may be increased as well if it is not in the full open position. To turn the nose to the left, lower the collective or apply forward cyclic. The throttle may be decreased as well if it is not already at flight idle. All right, so we'll hold off there. That is hold off there, page 17 and 24 in chapter 11. Next one we'll go over. So that was really landing with stuck or neutral right pedal, and that was landing with a stuck left pedal. Next one will be loss of tail rotor on page 17 and 24. See ya.